So this chapter is the first of a few chapters where we look at the different components of the Earth and some basic ideas behind the chemistry of each one. All right. Obviously, there's a lot to discuss, but the goal here is to give you an overview of each component. All right. Let's get this up here. There we go. So here you can see in this image here, you can see all of the parts and some sort of different aspects of each one, which I'm just going to discuss here. So the Earth itself, of course, is divided into several regions, all right? So, of course, there is the core. And of course, this isn't accessible. It's believed to be largely composed of iron and nickel. And the way they determine these things is to use the science of seismology and our understanding about how seismic waves move through different types of materials. So this is how they gather what the internal core is made out of. So it's not like we've been able to go there, right? So here you can see that here's your solid metal core. And then outside of that is the mantle, all right? Now, this is composed of silicates, all right? So we think back to, organic chemistry and all of it's based on carbon, except when we were talking about polymers, and we had polymers made up of silicates, right? Silicones. So there's lots of silicates, and they compose the mantle, and with that, metals. Now, of course, the part that we're most familiar with is the outer part. That's the thinnest part, of course, and that's the crust. And there's actually three parts to that. So that crust is made up of the lithosphere, and that's the land, okay? Then, of course, the hydrosphere, which we'll talk about later, is the water, and the atmosphere, which is the air or the gases that are surrounding the Earth. Okay, so that's what we're dealing with here. So lithosphere, right? And then you've got your oceans and you've got your atmosphere. So we're going to talk about each of these. All right, so of course here, since we're talking about Earth, we're going to start with the lithosphere. All right, so this is what's making up the land masses as well as the surface underneath the oceans. Okay, so this is what we're discussing here. And most of that is made up of these three components: oxygen, silicon, and hydrogen. All right, so oxygen, hydrogen, and silicon make up most of the Earth's surface. Okay. Now in my notes, you'll see some details. Not that I'm going to get you memorize these numbers, but if you look there, the core has a diameter of about 3,500 kilometers. The very middle is solid. The outer part is liquid. All right, it's solid because of the pressure that's involved here and the force of gravity. All right, the mantle is about 2,900 kilometers thick, so not as thick as the core. And there are different parts: the lower mantle, transition, and the upper. And as I said, made up of silicates, right, and different types of metals. Of course, iron is one of those main ones, all right? The crust, of course, is the outermost layer. So here you're talking about your land, water, and air, and I'm just looking, I don't have any other stats there. Okay, so let's talk about that lithosphere. So that lithosphere is made up of two parts that we could be familiar with. The inorganic portion, all right, and that's the rocks and minerals, okay? And then there's the organic portion, and that's the living organisms, then their waste, right? The organic materials are largely carbon, so notice the inorganic is going to be largely silicates and the metals, the organic carbon, and along with that, oxygen, nitrogen, and hydrogen, like we were talking about in organic chemistry, all right? So remember, lithosphere has an inorganic and the organic components. All right, now this, of course, is the part that we use to conduct our life, right? It is the part that we need to use to survive, and as a species. All right, so let's, we'll look at how we use them. We'll come back full circle as to how we need to now look after these different components that we need for survival. All right. So like I said, if we go back here, right, so the mantle consists largely of silicates, right? So, and that, of course, is what we're dealing with as well in the surface here, right? So here you've got your mantle silicates, and the crust is the outer part, and your land masses. And we're dealing, like I said, largely with silicates. Now, these silicates, they are basically what we call silicon dioxide, or SiO2, but their basic structure, right? And you might be thinking, why did you say SiO2 when we're looking at SiO4? It's because silicon, it combines with 4 oxygens to make this tetrahedron, and then it will combine then into different ways, different crystals or sheets. And you'll see, if you look through here, you're going to see different numbers of silicon and oxygen. So it gets summarized down to SiO2, all right? But basically, they're all made up of silicon and oxygen, and just the way they are arranged makes up the different types, okay? But if you look at a silicon mixed with oxygen, it can take on a tetrahedral structure, again, because silicon has the 4 valence electrons, and then oxygen, of course, would like 2 electrons, and it can combine with that silicon, and then it can then also then bind to the next tetrahedron, all right? So if we look at this, and then here we've got some listed. We're going to talk about some of these. So quartz, this is straight up SiO2. Here we've got muscovite mica, or mica. This is going to be in sheets. So here you've got these 3-dimensional crystals. Here you have sheets. Then you've got fibers, so double chains here. That would be in the asbestos. Then really, really long chains. You can see that we're adding different types of things. And then zirconium. This is a very simple anion that exists here, and then it combines with different substances. You can see the different uses. So different silicates for ceramics. Here's where we get our lithium from. Here, as you know, asbestos fireproofing. Of course, we don't do that now because these fibers can cause cancer. And then sheets for insulation, packing materials, and of course, making glass, sand, gemstones from those crystals. Right now, if you look first at quartz, you have a very regular arrangement of these tetrahedrons, okay? And you get these beautiful crystals, and it's very stable. We don't have any free electrons here. So it's not very reactive, which is something that's important to notice at present. And then you can see that there's going to be some color that's going to come from other metals that get mixed in here in different ways, all right? But basically what we're dealing with is a 2-to-1 ratio of silicon to oxygen, okay? Now, here micas, on the other hand, all right, now we have an SiO4 tetrahedral arrangement, so now it's like a 2-dimensional sheet, okay? And then we can change that to asbestos, and that one we're going to have a fibrous arrangement, okay? And here we've got a bit of magnesium in here, all right? So if you look at it, quartz was SiO2 just simply because of the arrangement of the crystals, and mica is SiO4, and asbestos is SiO4, and I just noticed in my notes I didn't put Si, but SO4. It's not sulfur, it's silica, so you can correct that. Then ceramics, what we're dealing with now is a mixture of aluminum silicates. So here you can see we've got aluminum silicates up here as well, but here now you're going to have aluminum silicates that can be shaped, and the different types of ceramics or clays will give you a different type of clay structure, all right? And these ceramics, okay, so ceramics, the clays, aluminum, silicates, the different types of arrangements can lead to many different types of applications. What you're looking at here is actually, I am learning ceramics, so I throw. So here you can see, and this is one of my pieces, by the way, you can see that there's different types, and this was news to me because I didn't know how this worked, but you can see that you can have an arrangement 1-to-1, where you have alumina sheet, and then a silica sheet, and then they're hydrogen bonded. And then whereas 2-to-1, right, you've got the two arrangements of the silica with aluminum in the middle, and then there. Then you can see here, this would be exchangeable. It looks like, you know, for actual conduction. So there's all kinds of interesting things. So in this case, this would be an insulator. In fact, a lot of wires are held with clay or ceramic forms, all right, because they will not conduct, all right. Whereas here you can see we have a different arrangement, and here you can have an exchange of cations, because it's a very different type of composite or mixture that we're having with our ceramic, right? So here you can see that in my notes, I'm referring back to my notes, you've got these different types of silicons mixed with aluminum, and you have different types of classes that you can have here, all right? So 1-to-1 clays are going to be tetrahedral. 2-to-1 clays contain some water. These are the ones that I would normally work with as when I'm making pottery. And then, as you know, they have to be fired in the kiln, and the water disappears. And then, of course, then it shrinks. With the water, it will expand, but once you get rid of it, then it will shrink. And then here you've got, with the 2-to-1 clays, sort of an octahedral arrangement, in contrast to the tetrahedral for the 1-to-1 clays, all right? Now, glass, on the other hand, this is non-crystal, and notice that compared to the quartz, the arrangement here is really weird, all right? And this means that this will have all kinds of, have the ability to take on different shapes, which, as you know, glass can do that with. And it is mixed with other elements, and you get different properties, okay? And so it says here, as you can see, the different properties or the colors in the glass can be changed by adding or replacing different types of elements. So soda lime, you can see here, ordinary glass for windows. Then you add in some boron. This would be heat resistant for like black glass that we have. Lead glass, this is what you'd find for optics. And then some colored glasses. So selenium will give you red ruby, cobalt will give you blue, chromium green, manganese violet, carbon, throw that in there with some iron, you get brown. And then you have photochromic glass. This is the one that has those elements in there going back to what we're talking about, redox chemistry. So you can have those redox reactions taking place there, stimulated by exposure to light. So you can see that glass, because it doesn't have a regular crystalline arrangement, it is pretty versatile, all right? And that's why when you heat glass, it doesn't just go to a liquid. It has this sort of point where you can shape it. And then once it cools, it hardens, all right? Okay, now cement and concrete, again, still we're talking about silicates, but now we're mixing in some calcium. So when you're talking about cement itself, you have limestone in there. We've got some clay, which, as you know, is aluminum silicates, and those are going to be mixed. And you can see that at one point, if it's heated, it's going to be called clinker, and that's going to be then ground up and mixed with some gypsum, and that will make cement, which, as you know, if you combine that with some water, and then you can see they put an aggregate, which is sand and gravel, that's going to harden to form concrete, right? Portland cement This is one that's heated with limestone, and then it's mixed with sand and gravel, and that's going to make, so it's a particular formulation of concrete, all right, and in the way that they put it together. And that more than likely changes the properties of that concrete, right? So again, cement and concrete. Cement, you got your aluminum silicates like you did with clay. You add in some calcium, and that comes from your limestone. So you mix this calcium carbonate with the aluminum silicates that you would find in clay, and you've got clinker, and that's going to then be mixed with gypsum to make your concrete. All right. Okay. Now, why do we use concrete so much, right? Really inexpensive. Look what you're dealing with. It's not like you have to purify anything to any great extent. So inexpensive, really strong, and as you know, durable, and really resistant to temperature changes. So it's really good for building, and that's why it's used that way, okay? But the problem is, and I come from a small town, actually, I wonder if I could, I'll see if I can put up a video of or a picture of it, but there's a lot of sand and gravel mining in where I come from, and it's really quite dramatic as to what happens for years and years and years, what happens to an area that's rich in sand and gravel, because it's what's needed to make your concrete, okay? So aggregates. And of course, then when you're making cement, there's some heating involved, as you can see here, cures and hardens. Making Portland cement, you can see when you're making that, there's going to be some cost involved in terms of energy to make that, and there's going to be some carbon dioxide given off, lots of particulates. It's crazy how much dust there is where I grew up. All of this from this mining aspect of that. Yet, it's really interesting that those kilns that they use to make the cement are hot enough that they can break down things like tires, and that toxic waste that comes off of that is actually able to be broken down, and it's really quite an ideal way to recycle tires or get rid of the tire waste. Now, in terms of metals, of course, we need metals, and in fact, they're so important to our history that we actually classify our ability to harness these different types of materials from the ground as to how far we have come historically, right? So Stone Age, Bronze Age, Iron Age. So clearly bronze and iron, that tells you that those are the times in our history as human beings that we were able to figure out how to extract and then use those materials for tools, right? So copper was one of the first ones that was could actually be found as its own, right? But then it was also then the first one that was extracted from an ore from rock by smelting. All right, and it then became the main ingredient of bronze. So that's the Bronze Age, right? So smelting is a way of getting the metal out of the ore by heating it. So melting it away from the rest of what's there. Okay, and very often it will be contaminated with some other stuff. So I've got a couple of things listed there for copper mixed with sulfur. All right. But we were able to figure out how to do this, and I mean now we know we use copper for water because it's a conductor, right? Then iron, of course, Iron Age. This is probably one of the most fundamental. We use iron in so many ways. We have lots of it in the ground, but the thing is, it combines with oxygen and sulfur. So in order for us to use it as an iron ore, it has to be removed from the contaminants, and again by heating, so smelting it. And when that happens, you're heating it. You start off with the ore, and that ore is called hematite, all right, because it's mixed with oxygen. If you think of your body, your ability to carry oxygen is carried by hemoglobin, right? So this is the mixture of iron and oxygen, and when you think of heme. And of course, biologically, there's a structure involved with that. But one has to try and extract that oxygen from the iron so that it can be done. And that's done in a blast furnace. And one of the first steps involved with that is to try and get that oxygen out of there. And the way to do that is by mixing it with a really pure form of carbon. All right, so what they're doing, so they'll actually take coal and they'll make coke, which is a very, very pure form of that carbon. And that can then be converted in the coal through heating to carbon monoxide. And as you know, that's a poison, but carbon monoxide, and that is then mixed with that hematite with heating to get your pure liquid iron, as you can see here, and you're going to give off CO2, all right? But this is how we get the oxygen out of that ore, because it can combine so well with carbon. And then again, mixing that with the iron. And then out comes our pure liquid iron, okay? Where is that done? Well, it's done in the blast furnace, okay? Then ultimately, this iron is very often used to make steel, all right? So if you look at this, and here's the whole process in this blast furnace, it's kind of simplified down here, but remember, if one of the first steps is to make coke, right? So you're gonna take coal, make a very pure form of that, mix it with oxygen to make carbon monoxide. So you can see that that's one of the first steps here. Carbon monoxide is being produced here. And then what's going to happen is that it's going to be mixed with the iron, and you're going to get out CO2. All right, so here you're going to mix that iron with that carbon monoxide, and you will then be able to get out your molten iron, okay? Now, the next part is to use limestone, all right? Limestone is gonna try and get rid of the silicate impurities, because again, remember, you're getting this out of the ground and it's largely silicates, so you have to get rid of those, all right? And those can be removed using limestone. All right. So when you do that, the silicate and those impurities, okay, they are pulled off as molten slag, right? And that's quite, striking if you see that slag come off from a place where they do this at night. Okay, they do that very close to where I grew up as well. And anytime you drive past that area, this is Burlington, Ontario, at night you can see the slag. And then after that, that's less dense than the actual molten iron. So that will be drawn off on the bottom, the slag off the top, okay? And at the end of the day, then you have your pure iron. And this sort of makes it look all in one sort of step. But of course, it's going to be done in different ways, okay? Now, cast iron then, we use that as well. But now, to make steel, it's alloyed with carbon, all right? And there's going to be different types of steel, and they can be then mixed with other types of metals to get your final product, as to what kind of steel you want. So here I've listed some from your text. So tungsten steel, really high strength, molybdenum steel, where at resistance, nickel steel, strength, manganese steel, hardness, stainless steel, as you know, that's the one that doesn't corrode. So there's some chromium and some nickel in there. So there's many different types of steel, but they're basically all combined with something in carbon. All right. Now, another very high metal that's found in the not in the atmosphere, in the earth, is aluminum. And in fact, it is the most abundant metal that we have in the crust. And the ore that contains the aluminum, so the impure aluminum, is called bauxite. And that aluminum oxide is removed from its impurities, all right? And here it can be done with a strong base in order to do that. And with an electric current, and out it comes. So you get this molten oxide to produce molten aluminum metal, right? So here you've got your reaction. And then again, there's all kinds of different types of metals that some of them I didn't even mention here, and what they're used for, right? So you could see indium, lithium, palladium, platinum, rare earths, right? And where they often come from. And some of their uses, all right? So, but the main ones that we think about, of course, because first of all, obviously copper, and then iron, right? And then, of course, aluminum. And like I said, it's the most abundant, okay? Now, let's see. I'm just going ahead in my notes here. Make sure I'm not saying things that I should be. Okay, so now, obviously, all of those metals and ores and all silicates we have a lot of, but a lot of the other metals, you know, there's only a certain amount that's available in the earth. And as you know, you can't create matter. It is what it is, all right? And this slide here just lets you know that as we get more and more people, there's more and more demand for all the things that need these metals. And with time, we're getting the high-grade ores are gone, but our desire for those metals is not only not diminishing, it's increasing. So then you get lower grade ores, and then they have to be extracted, and that, of course, is more expensive, and there is more of a cost to the environment, all right? This is why they're turning to the oceans, of course, to look for more sources. But we're still increasing our population, and that's sort of, you know, the point of this slide. So what do we do about that? Because this is clearly not a sustainable system, all right? So this is where you get your reduce, reuse, recycle. Try to reduce the amount that we need, right? Even though, you know, we are consuming, right? Somehow we have to try and reduce the amount that we're disposing of, so that we can do the other two things, right? You can see here 30% of solid waste is recovered or recycled, 14% incinerated, but 56% is just thrown out. I don't know about you, but I always imagine that in the future they're going to be mining our landfills for all of these things that we just got rid of, and we never bothered reusing or recycling. So then, of course, reusing, that's what I was just saying. So how does that work? Well, that's, you know, reusing the materials is going to, you know, save energy for producing new ones and extracting them, right? And finding ways to do that. And then, of course, recycling, that's going to reduce the waste. But if you're going to recycle, there is a cost. You've got to ship those substances, and you've also got to very often apply heat to do that. So that's going to be the energy cost in order to do that as well, right? So these are all things that we have to figure out how to deal with. And this sort of is going over like our waste, and you can sort of see where it comes from. You can see 8.8% is metal. You know, then you've got your glass, right? We might not worry as much about that because it's, you know, silicates are, you know, a lot, but still, there is going to be a cost to that. And we already talked about plastics and the problems with that. So, you know, just something to think about as we move forward, because we all have to deal with this as a species. And that's about it. So hopefully that's a good review of what we discussed in class. And then we'll move on to chapter 13.